Throughout time, explosions in the universe have shaped our very existence. The Large Hadron Collider in Switzerland has been created to help us understand these shaping events. Here, protons are being smashed together at nearly the speed of light with incredible energies. These collisions on a small scale can recreate the earliest moments of the universe. All that exists was born in this ultimate moment. 1/1,000,000th of a second. That's how long it took the universe to go from the Big Bang to one of the most important events in its entire 13 billion year history, the formation of the first proton. Protons weren't around at the instant of the Big Bang, but they have played a key part in nearly every explosive event that's happened since. This journey follows a single proton to take us through some of the universe's most violent moments, from immense calamities on the largest of scales to the eruptive events that have shaped the Earth. As the universe expanded and cooled, these particles began to form atoms, the building blocks of all the matter that we're familiar with today. Many of the protons that formed right after the Big Bang are still around today. They normally hang out in the center of atoms, where the positive charge attracts a cloud of negatively charged electrons. The simplest of these atoms is hydrogen, a lone proton orbited by a single electron. The most important element of the universe has now been formed. After the Big Bang, as the universe cooled down, the hydrogen that was formed began to clump together into clouds of gas. Within these clouds, some of the first stars to form were monsters. They were dozens of times the mass of our sun. As their hydrogen fused into helium, they burned with such intensity that they glowed blue. Around these stars, there were no heavier elements, no solar systems made of rock, metals, and dust. Just unimaginable heat and pressure. The first stars voraciously consumed the hydrogen at their cores. When the hydrogen was depleted, they then started burning helium and subsequently heavier elements. But with each step towards heavier atoms, less energy was released by the star's fusion. Ultimately, this fusion could no longer overcome the inward pull of gravity, and the star's core collapsed. And metals were produced in this blast, even as the star that gave birth to them was destroyed. Eventually, these heavy elements seeded surrounding clouds of gas, clouds that could later give birth to stars of their own. The collapsing core became so dense that the space around it became distorted. A black hole was formed that not even light could escape. Typically, black holes that form in this manner start out many times heavier than our Sun. But black holes near the centers of the earliest galaxies weren't typical. They had so much to feed on that they became gargantuan. They consumed clouds of hydrogen, the earliest stars, debris from other explosions, and even in some cases, other black holes. These monsters are called supermassive black holes, and a single one of them has the same mass as millions of suns. The jets of matter shot out by a galaxy's central black hole are so bright that they can produce more light than an entire galaxy full of stars. That brightness lets us observe them at the distant edges of the universe, making them some of the farthest objects we've ever seen. The energy involved is so large that it can blast our proton, along with other matter, clear of the entire galaxy. Even if our proton finds itself ejected from the galaxy it called home, it wouldn't necessarily mean that things would go quiet. For starters, it could have a lot of company. Gravity can draw huge clouds of gas together. But gravity doesn't just attract gas. It attracts other galaxies as well. Even today, our Milky Way galaxy is still drawing matter and stars away from smaller companion galaxies. And 4 billion years from now, it'll slam into our nearest large neighbor, the Andromeda Galaxy. What would a galactic collision look like to our proton? Even though the gas clouds between galaxies are far less dense than our atmosphere, they can still move nearly 200,000 miles per hour. When they slam into the clouds of other galaxies, violent compressions occur at the collision sites. These shock waves compress and heat the gas, causing it to glow. Sometimes the gas is so hot that it glows with ultraviolet light and X-rays. As the galaxies collide, the shock waves move deeper through the rich clouds of gas within a galaxy. As they do, the force of the shock causes the clouds to collapse, leading to a new wave of star formation. Over millions of years, the ignition of new stars can be like a sea of candles, illuminating where the gas clouds collided. The gas clouds turn out to be where all the action is. The stars themselves are so far apart that they pass by each other during the collision. Their paths are curved by gravity, and it is this gravity that eventually draws them back in, thus completing the merger. This newly merged galaxy will start out badly distorted, but over time, it gradually smooths into a clean elliptical one. Having been carried into our galaxy by the shockwaves of that collision, our proton is now traversing the edges of one of our spiral arms. It is here that we get to witness an incredible cosmic recycling process. Most of these later stars are smaller than the original stars of the early universe. They come in many sizes and temperatures, as indicated by their color. The largest of these will die in spectacular explosions called supernovae. But not all supernovae come with the same personality. One, known as a Type 1a supernova, is created in a binary star system. Here, two stars are orbiting around a common center of gravity. The smallest star is a white dwarf, a star that's already reached the end of its life. Its companion star, the larger one, is close enough that the white dwarf is stripping matter from it. When enough mass piles up on the white dwarf for it to reach a critical density, there is enough uncontrolled fusion created and the star detonates. Supernova explosions seed the galaxy with all the chemical elements heavier than iron. Gas clouds are now contaminated with all sorts of complex molecules. And if they collapse to form a new star, that star won't be alone. Blown into another region of our galaxy by the shock waves of the supernova, our proton has now found its way into the remains of a large cloud of gas and dust. This cloud is the remains of a former star that went supernova early in the Milky Way's history. It is here, almost 5 billion years ago, that the proton took part in the birth of our solar system. The solar system started out as a huge twirling disk of gas and dust. Over time, however, the hydrogen and helium near the center of the disk collapsed under gravity to form the Sun. Some distance away from the center, our proton acquired an electron and became a hydrogen atom. It also found itself attached to an oxygen atom as part of a water molecule. Everything was a jumbled mess of ice, rock, and gases. Over time, these materials collided with each other and merged, forming larger bodies. In the outer solar system, the hydrogen and helium gases were cold enough to be pulled in by the gravity of these rocky bodies. Eventually, they cloaked the solid cores beneath enormous envelopes of gas. These gas giants eventually dominated the outer solar system, gradually sweeping away or capturing many of the smaller objects that crossed their paths. Closer to the Sun, violent and energetic collisions continued. Pieces of matter eventually merged themselves together into a collection of rocky bodies called planetesimals. Most of these planetesimals were under a mile across. Water in the early solar system, like the molecule our proton resided in, was scattered from object to object through these impacts. The era of planetesimals was a temporary phase, the terrible twos of our solar system. Through these collisions, some gentle, some violent, a number of these objects accumulated more and more material. Eventually, they became the first protoplanets. As the protoplanets grew, they eventually dwarfed the planetesimals. Collisions between them were no longer world-shattering events. Protoplanets were big enough that they easily absorbed the smaller bodies that hit them. Planetesimals could still leave impact craters and scattered debris, but most of the material would simply stay where it hit, thus adding itself to the protoplanet's mass. In the inner solar system, a tug-of-war between Jupiter and the inner planets shifted the orbits of bodies into unstable paths. One of the largest, a Mars-sized protoplanet, was catapulted directly into the path of the oncoming Earth. Was massive. All of the liquids and gases of the Earth were vaporized and driven off into space. Temperatures rose so high that some of the Earth's rocks not only melted, but actually evaporated. Iron from the impact had dissolved into a molten sea. This sea plunged through the molten debris of Earth and ended up at its core. Debris that was flung up into orbit coalesced into a molten ball of rock. Eventually, this ball formed into a moon that orbited around the reborn Earth. Both bodies remained molten for many years, slowly forming crusts that covered their still glowing interiors. Eventually, the inner rocky planets of our solar system emerged, and over time they swept away most of the smaller objects left near their orbits. Earth picked up its share of material from these other bodies. Bodies such as comets rich in water and meteors rich in carbon and complex chemicals. Water, including the molecule containing our proton, made the Earth blue. Gases released from Earth's interior became an atmosphere, and trace amounts of precious metals were sprinkled on top of its crust. Within 500 million years, this remaking of the Earth gave rise to life. With time, this life turned the land green, put oxygen into the air, and diversified itself into countless amazing forms. Over the ages, our planet's gravity has mostly swept the area near it clean, and the giant planets of the outer solar system have thrown legions of small intruders out of the solar system. But every now and again, a large object slips through. "65 million years ago, one of these stragglers found its way to Earth, crashing just off what we now call the Yucatan Peninsula. planet in darkness. Shockwaves, tsunamis, and massive fires all rain destruction near the impact site, with ecological disruptions echoing across the globe. When it was all over, the majority of all life on Earth, like the dinosaurs which had dominated it for millions of years, was gone. Huge blocks of our planet's surface have been in constant motion for billions of years. Known as tectonic plates, they slid past each other, slammed into each other, and then slowly separated again. Some of these plates ended up shoved below a neighbor and pushed down into the molten interior. Underneath them, large pools of lighter substances gathered, searching for a path to the surface. Our proton, trapped below, was forced up through cracks and fissures. It finally reached a vast underground pool of magma. Some of these pools would grow into enormous molten underground lakes, trapped miles beneath the surface. The heat from this subterranean molten rock kept the planet's surface active, littering the landscape with geysers and scalding hot springs. But the magma itself was sealed in. As more and more magma poured into the underground pool, it stretched the surface of the Earth above it. Eventually, the surface failed completely, releasing the pressure on the entire reservoir of magma below and exploding it upward. The result is what we call a supervolcano, and the magma, now lava, cooled into ash. Even many miles from the eruption site, volcanic ash quickly buries large parts of the landscape. The amount of ash ejected by supervolcanoes can be thousands of times more than that released by a typical volcanic eruption. Nearby ecosystems would be devastated, and life throughout the continent would be adversely affected. Hot ash would rain down, and its choking clouds would darken the sky. The destructive after effects of an eruption like this would not only be widespread, but long felt. Volcanic ash would stay high in the atmosphere for years, cooling the planet and possibly even triggering an ice age. It could be centuries, if not millennia, before the Earth's climate would return to normal. Today, the planet is far more peaceful. There hasn't been a supervolcanic eruption that has affected humans for close to 70,000 years. Collisions are uppermost in the minds of researchers on the border of Switzerland and France. Here, scientists are destroying protons to help us understand the very birth of the universe. These protons start out as a cloud of hydrogen gas. Then their electrons are stripped away, leaving bare, positively charged protons. These protons are accelerated to nearly the speed of light. And then they are pushed through a series of rings that boost their speed even higher. Finally, they are accelerated into the largest ring humanity has ever built, the Large Hadron Collider, or LHC. The LHC has a circumference that's over 26 miles long. When the atoms are fully accelerated, they'll be circling around it at over 11,000 times a second. By then, each bunch of 100 billion protons in the beam will carry as much energy as a 450-pound cannonball traveling 80 miles per hour. The LHC actually has two paths through its tunnels. These cross each other 4 times, separated by about an inch. This enables some of the protons to collide with each other. As these particles collide, the quarks inside of protons interact with each other, creating a soup of exotic particles that exist briefly before dissipating like a tiny puff of smoke. In that brief instant of existence, it takes us back to that tiny fraction of a second after the Big Bang, to the material that formed the first protons and which started the universe. It is the ultimate realization that out of devastation comes new creation. A process of renewal that reveals how our planet came to be, and the discovery of how those violent forces eventually transformed Earth into the life-bearing world we call home.